In this question, we were told it's about the kinematics of an elevator. We're first asked to explain the difference between gravitational mass and inertial mass. The main thing to know about the difference between the two is that the difference is in how they're determined. Gravitational mass is determined from or by its gravitational effects. For example, the force of gravity. Inertial mass is determined by its inertia, resistance to a change in motion as measured by its acceleration. And Newton's second law. Both values of mass, the number, should always be the same as mass is the amount of matter in an object. No matter how it's determined. Subtle distinction. Newton's second law is F net equals ma, so that mass is determined by the accelerations and the forces, whereas the gravitational mass is determined by the force of gravity. So that is our first question. Second part B, we have a graph. And so the first thing we're going to do always when we see a graph is do Oy-Zerga on this thing. So we have O, Y, X, I, R, G, A. The origin is 0, 0, check. The y-axis is velocity. And we see it's in normal units. And there are 5 increments. So this goes by 0.02, 72, 74, 76, 78, 80. The x-axis is time in normal units, and we have 1 is the numbered scale, and there's 1, 2, 3, 4, 5. So this is by 0.2. The intercepts, yes, there is a y-intercept at 0, 0, and there is an x-intercept later at time 12 seconds. T equals 12. The quantities we can read are the axes, velocity and time. The gradient or slope is delta V over delta T, which we should recognize as acceleration. And the area, V times delta T, is the displacement. So now we've set ourselves up to be able to answer any question. We're told the mass is 250. We want to use that to calculate the acceleration of the elevator during the first 0.5 seconds. So our Oy-Zerga tells us acceleration is the slope. The slope during the first 5 seconds. We want to say explicitly acceleration is the slope. So the rater knows what we're doing. So if we made a mistake mathematically, they would still know we understand. So acceleration is delta V over delta T. This point here is 0.5 because that was given. And we see it's halfway, 0.2, 0.4, 0.6, 0.8, 1.0. And 0.80 meters per second. And the point down here is 0, 0, the intercept. So we have the change in velocity is final 0.80 minus the initial, which is 0 all over delta t, which is 0.5 minus 0.0. And 0.8 divided by 0.5 is 1.6 meters per second squared, and that is the acceleration. 2 significant digits is the most we can report. So that is how we obtain the acceleration from this graph. The total distance traveled by the elevator is the next question. The distance, I go back to my Oizerga, is the area. So we want the area, the total distance traveled by the area. And so it starts from rest on the ground floor. It comes to rest at a higher floor. So we see it starting at 0, it increasing speed, then traveling at a constant speed, then slowing down, and coming to rest after 12 seconds. So the three shapes that we see, three shapes here. There is a triangle here, a triangle here, and a rectangle betwixt the two. So the total distance is the area. Again, making it clear to the raters we understand what we're doing, even if we make a mistake. And that area is going to be the area of this triangle plus the area of that triangle plus the area of the rectangle. So that area will be 2 times 1/2 base times height. And to make sure we see they're the same, we have the midpoint, there. So that is 0.5 seconds indeed to 0.8. And the rectangle then is going to go from 0.5 to 11.5. So that is 11 seconds. So this is length times width. So those cancel. The base is 0.5 and the height is 0.8. And the length we said was 11 seconds, and the width is 0.8, which gives us 0.4 plus 8.8 equals 9.2 meters. And that is the total change in height. Next, we're asked to determine the work to raise the elevator to a higher floor. Well, we have the elevator like this. And so this is the work goes into the change in gravitational potential energy. And so that is mg delta z. The mass, we are told, is 250 kilograms. Gravity is 10. And delta z we just figured out is 9.2, which gives us a nice even 23,000 joules, which the work then would be 23 kilojoules. And that way I'm expressing the proper 2 significant digits. Next, we're asked to determine the power. The power is the rate of doing work, the work over time. Well, the work we just figured out, which is 23,000 joules, and the time it took for that to occur was 12 seconds. Exactly 12 seconds. And that works out to be 1,916.6 watts. We can only report 2 significant digits, so that power is going to be 1.9 times 10 to the third watts, or we could say it's 1.9 kilowatts, and that is the power. Lastly, we are asked to determine the efficiency of the motor. The input power is 5 kilowatts. So here's what's happening, is we have a motor that is putting out 5.0 kilowatts, but the work being done is only 1.9 kilowatts. So we can get a sense that the useful work being done is far less than the work being put out. And so we would say then the efficiency is the work out divided by the work in. And so that's 1.9 all over 5.0, which works out to be 0.38 or 38%. And that, my friends, is the efficiency of that motor. On to part C. We have another graph, the same graph it looks like. And we are asked to sketch a realistic variation of the velocity for the elevator. And so the simplified version is shown as the dotted line. Well, the first thing we know is that this line represents a constant acceleration. Constant slope equals constant acceleration. And so we have a constant acceleration like this here, and then no acceleration. Is it possible for something to just stop accelerating like that quickly when it's a motor? And so the answer is no, it's very unlikely to be that this should be smoothed out a little bit. There's some jerk that goes on. When we go from constant velocity to accelerating, there has to be some kind of jerk because the acceleration changes from something to zero or zero to something. And so if there is a delta A over delta T, that means there's jerk. So that must happen here in the beginning, at that turn there. It must also happen here. So probably there's an inflection point like this, and it ends up being a little steeper. And so what I'm doing in a kind of exaggerated way is it's probably more like something like that. And similarly, we would have that over here. Some people might refer to that as giving it shoulders, like so. So that is part C. We will finish the question in the next installment.